Welcome back. In this episode, we will discuss about the implementation of logic gates using 2 cross 1 or 2:1 multiplexer. Before going to know about this thing, we will see what is the generalized view of multiplexer. See, this multiplexer has 2 power n inputs and n selection lines are control inputs and finally 1 output. See here, the selection lines S0 to Sn means if n is equals to 3, then 2 power 3 inputs are available. If n is equals to 1, 2 power 1, nothing but 2 inputs only available. So depending on the selection lines, we have the inputs. Also, a multiplexer is a logic circuit that accepts several data inputs and always one of them at a time to get through the output. That means the routing of the desired inputs to the output is controlled by the selection inputs. That means if S0 is selected, then A input will be connected to the output. If S1 selected, then B input will be connected to the output. Like that it goes on. That is called the multiplexer. Now we will see 2:1 multiplexer. Nothing but 2 power 1:1 multiplexer. It has one control input, that means n is equals to 1. So 2 power n is equals to 2 power 1. Nothing but 2 inputs are available at the input side. Always we have only one output in any of the multiplexer. See this multiplexer. If s is equals to 0, A will be selected. So whatever it is the input, that input will be transferred. So y is equals to A. Simply we can say if A you have given 0, the 0 will be transferred to the output. Similarly, if you given A input as 1, that 1 input will be routed to the output or 1 will be transferred to the output side. It all depends on the selection line. Now we will see another case. If S is equals to 1, B will be selected. That means the B will be transferred to the output. If B is equals to 0, then B will be transferred to the output, as well as if B is equals to 1, that 1 will be transferred to the output. So whatever it is the either A or B, depending on the selection line, it will be transferred. So finally, the logic expression for this 2:1 multiplexer is y is equals to S dash A plus SB. With this knowledge, we will design the AND gate with 2:1 MUX. You know that the logic diagram of this AND gate is like this. Inputs are A, B. The logic function is y is equals to A dot B. So that means the multiplication. Here the property of the AND gate is if both inputs are 1, then only the output is 1, else 0. See here the truth table which is having inputs A, B, the output is Y. In the last case only we have the both inputs 1 and output is 1. In remaining all the cases it will be the 0. So once we find the truth table, from the truth table we can design the AND gate like this. See here the first row A is equals to 0, that means S is equals to selection line A is equals to 0, irrespective of the B input, the output will be the same as A. So output follows A input. Thus 0 will be transferred to the output. From the truth table you can design like that. In similar fashion, see here the A last rows A is equals to 1, that means selection line A S is equals to A is equals to 1. So B follows the Y. So B transferred, the B will be transferred to the Y. So whatever it is the input 0 will be transferred to the output Y, 1 will be transferred to the output Y. The logic expression is Y is equals to S dash A plus SB. Instead of the S you have to put A. So it becomes A dash into A plus SB, right? So instead of the A, we have already given A is equals to 0, so that it becomes 0. And another term is SB. Instead of this, if you put A into B is the only term we have. So finally, this AND gate with 2:1 MUX realized.